Hello, everyone, and welcome to my lab. I want to share with you the excitement and the joy of doing science. I want you to be on the lookout for all kinds of different changes. I want you to make as many observations as you possibly can, and I want you to make sense out of these observations. So we'll move on and do the same experiment, but with this yellow balloon. You've already seen and heard what happens when we put a flame to a yellow balloon. And maybe the color of the balloon has something to do with it. Maybe it doesn't. Let's try to find out. So we'll do the experiment by bringing the flame closely and slowly to the balloon. You ready? And that balloon had in it not helium gas, but hydrogen gas. And hydrogen is a very flammable gas. It is, in fact, a gas that combines with oxygen that's in the air very violently. Now, what we like to do in science when we do experiments, we like to repeat the experiment. So we're going to repeat this experiment one more time, but we're going to do it in the dark to see if we can make some different kinds of observations. So let's do this, and let's do it in the dark. Here we go. There's the flame, and there. You see that ball of fire? That ball of fire was the combustion of hydrogen combining with oxygen that's in the air. And what we're going to try to do is to look at this now in slow motion. So focus your attention on the replay. It's going to be without sound, of course, and you'll be able to see, but not hear, what this reaction is all about as we look at it in slow motion. There it is. There's the flame coming to the balloon, and there is that great ball of fire, and you see how beautiful it is. We could learn more when we do the experiment in the dark than we did with the lights on. So now, you being good observers and also obeying the safety regulations, you noticed that in addition to the release of energy in the form of light, there was the release of energy in the form of sound. And we want to be protecting our eardrums from potential damage. So what I would like you to do is to take both fingers and stick them in your ears very tightly, so that as we move on to the next set of balloons, just in case there is more sound energy being released, we have our eardrums protected. Now, I cannot do the experiment and have my eardrums protected and use the flame at the same time, so I brought with me some earplugs. And so I'm going to put the earplugs now, and I want you really to protect your ears very, very well. If you can hear what I'm saying, that means you don't have your ears well protected. I can't hear you, but I can see you smiling and laughing. That means you can hear me. So make sure that your ears are very well protected as we go on to the next set of balloons. And you ready? Here we go. That balloon had in it a mixture of hydrogen and oxygen. There was a lot more oxygen in close proximity, in the same vicinity as the hydrogen, and that's why the reaction took place, this combustion reaction took place and released not only light energy but sound energy. And of course, what we like to do is repeat the experiment, and let's do that one more time in the dark. But I want you to protect your ears very, very well as we move on. Make sure your ears are well protected. Here is the flame. Now, that again showed us, when we looked at the experiment in the dark, showed us that we had the release of energy with a very loud report, that sound, but we also saw the difference in the flame. Actually, let's take a look at it in slow motion and see how we can compare that explosive reaction of hydrogen and oxygen in the same balloon compared to hydrogen in air by itself. So we'll look at the replay now in slow motion. You won't hear any sound. There's the flame from the torch coming up to the balloon, and there is. See, there's a difference in color, among other things that we will have observed. All right, so now let's look at another source of ignition. And what we're going to do is use this device, which is called a Tesla coil, to ignite, possibly ignite, what's in those plastic bottles that are in front of me. You notice that we have 5 plastic bottles. They have 2 nails. Each one of them has 2 nails stuck to the sides, and the nails are separated by a distance of about 1 centimeter on the inside. There's a cork on top, and then there is a clear and colorless liquid which you cannot see at the bottom of each one of these bottles. So we'll use this discharge device. You can hear it, and we'll try and have this discharge jump across the gap between the 2 nails. So we'll see and hear what happens. That is an example of the conversion of chemical energy into mechanical energy. And of course, we'll talk about that in just a second. Let's try to repeat the experiment one more time. Here we go. There you see. Did you catch that? You see, maybe the size of the bottle has something to do with it. Let's do it one more time with this intermediate size bottle. What we have in those bottles is ethyl alcohol, and it's the vapor of ethyl alcohol that's being ignited by this discharge from the Tesla coil. This is a simulation of what goes on inside the internal combustion engine, except in the internal combustion engine we have a fuel, which is gasoline. And gasoline vapor burns, helping us then change, or causing chemical energy to change into mechanical energy. And the ejection of the cork that we see, actually let's try to take a look in slow motion to see if we can watch the cork being ejected. So take a close look now at the last experiment I did, and see if we can see the cork being ejected. There, just flew right off the top there. Well, we've got 2 more bottles here, or 2 more plastic bottles, and those are bigger, of course. So let's do this experiment. In fact, let's do this experiment in the dark, all right? The last 2, we'll try to do them in the dark, so we'll watch and see what happens. Here we go. Here we go. And with the lights on, you could see that these are examples of uncontrolled combustion reactions. Of course, in the internal combustion engine, we use additive to the gasoline to control the smooth movement of the piston, because we want chemical energy that's being converted to mechanical energy to do some useful work for us. What I would like to ask you to do now is to focus your attention on these dishes that I have here. And inside these dishes, I have some wet towels that are, one in a clear and colorless liquid, and the other one is in a clear but colored liquid, and you can tell what the color is. I'm going to take one of these towels out. Actually, I'm going to just dry it out a little bit like this, open it up, and then I'm going to take the other one and do the same thing to it. And hold one like so, and the other one like so, and then we're going to put them on top of the flame and turn off the lights, and let's see what happens. And you see that the towels Okay, now with the lights on, because I wanted to see that the towels, for the most part, are not burning. Except for this one, it's really, well, it's still going on. And we've got to be careful about this. We still have that fire extinguisher handy, right? We're not going to have to use it, but if we have to use it, we will. And we'll wait until this goes out. These reactions are reactions where the liquid in which the towel was submerged actually burned. And this is still being, well, smoldering a little bit here. So what we're going to do is I'm just going to drop it here and step on it and snuff it out.
Coming up, Professor Shakhashiri gets some help from University of Wisconsin mascot Bucky Badger in answering the question, how do Hollywood directors make London fog?
What I'd like to do now, as I allow the sublimation process to take place, is to ask you to focus your attention on what I have in front of me. What do you see I have in front of me? These are glass cylinders, and how many do I have? 2, 4, 6, 8, and they're arranged in pairs by the color of the liquid that's inside the cylinders. I'm going to take some dry ice, again, put the gloves on, and drop chunks of dry ice into those cylinders in a very special way. And you watch carefully what this special way is as we do this experiment. What's the special way that I'm doing here? Did I put the dry ice in every cylinder? In every other cylinder. And a lot of interesting things are happening. You see many, many different observations can be made. You see the gas bubbles? That's the carbon dioxide that's coming from the dry ice. You also see that the color of the liquid in some of the cylinders is changing. You can make a comparison of what the color used to be by looking at the cylinder of the pair where I did not put some dry ice. Now, carbon dioxide dissolves in water to form carbonated water. It reacts with water to form carbonated water, which has in it carbonic acid. And all carbonated beverages have in them carbon dioxide. A very interesting thing is happening in this cylinder. You see there's a lot of foaming at the top, and a very fascinating set of color changes are taking place. Now, what does this stuff look like that's coming off the top here? It looks like what? It looked like smoke, but it's not smoke. Is somebody else? It looks. Somebody said steam. You can't. No, steam is an invisible gas. You can't see steam. It looks like fog. That's what it is. It is actually fog. You know what fog is? Fog is condensed water vapor. And the condensation of the water vapor is taking place on the carbon dioxide that's escaping. And you notice that the movement of the carbon dioxide gas and the fog is in a downward direction. This movement tells us that carbon dioxide is heavier than air. What I'd like to ask that we do now is to go back to this beaker, and let's try to see what happens if I try to pour some of the carbon dioxide out of this beaker. You see the flame went out, and we repeat the experiment right here, and the flame went out here too. From this set of observations, we learn that carbon dioxide does not support combustion, and that it's also heavier than air because I was able to pour it out of the beaker. A whole bunch of different experiments can be done with dry ice and carbon dioxide, and I've done a couple of them now. I want to do one more. I'm looking for some hot water. I need some hot water to do the next experiment. Can I get some hot water? Somebody help me with some hot water, please. Ah, thank you, Bucky. Thank you, Bucky, and welcome to my lab. Thank you for the hot water. I know this is a busy time of the year for you with all kinds of activities that you have to deal with, because I know you are a very good science student, aren't you? Right, and you like science? And maybe someday you'll think about becoming a scientist. Who knows, right? Well, in case you decide not to become a scientist, at least you want to develop an appreciation and some understanding of what science is all about, don't you? All right, Bucky. For that reason, and I've known you now for 22 years because you've been coming to this special lecture for that many years, I wonder if you can stay for the rest of the program. Can you? You want Bucky to stay? All right, Bucky. Come on. I have a special place for you. I have a special place saved for you here. Actually, one of the best seats in the house. Just make yourself comfortable, and you make sure that you keep an eye on the experiment so you get to learn about what's going on. In fact, Bucky, if you had eye protection, if you had goggles, I might ask you to help with some of the experiments. Maybe we'll do that next year. All right? Okay. We'll go on now and take the hot water that Bucky brought, and we're going to put the hot water in this empty dish pan, which I will put over here. Here's the hot boiling water, which I'm going to add to the dish pan. You see anything coming off the top? No, no, no. Steam is an invisible gas. You can't see steam. It is condensed water vapor, right? That's what it is. You know, when you blow your breath on your hand on a very cold day, don't tell me you see steam. That's not steam, right? It's condensed water vapor. What we're going to do is take dry ice and add it to this hot boiling water. We'll see what happens. Now what does it look like, huh? This is how they make fog in the movies sometimes. They take dry ice and hot water, and once again you notice that the movement of the fog is in a downward direction, reminding us that carbon dioxide is heavier than air. You also notice that at the very beginning of the experiment, the cloud, the fog, did not move downward, but moved upward. And I wanted to think about that and think about the conditions of the experiment to try to explain what it is that we are observing here.
Coming up, some experiments you can do at home. But first, how do you fill an upside-down flask with water? We'll show you, so stay with us.
Now, just as carbon dioxide dissolves in water to form carbonic acid, other gases dissolve. And one of the gases that we want to look at next is ammonia. Ammonia gas dissolves in water, and I want you now to look at this assembly where you have a large round bottom flask with a clear and colorless liquid in it. You know, a lot of people confuse the words clear and colorless. They don't mean the same thing. This is a clear and colorless liquid, and there's another inverted round bottom flask up here that has in it ammonia gas. Ammonia gas is also colorless at room temperature, but it does have an odor. We can't smell it now because this whole assembly is sealed. I'm going to squeeze a little bit of water from this bulb into the top round bottom flask, and we'll see what happens. Ammonia gas is dissolving in the water, and it's causing a partial vacuum in the upper flask, and the liquid is being siphoned from the bottom flask to the top flask. And we added an acid-base indicator, again, to show us that ammonia is a basic substance in aqueous solution. Now, a whole bunch of different experiments that we can do, you can do, in fact, at home with acid-base indicators. And that's what we're going to do next. I'm going to take these candles out of the way and use household chemicals now so we can do an experiment together. What is this? Well, it's not just cabbage. It's red cabbage, right? It's red cabbage. Not only do we want to make valid observations, but we want to describe our observations accurately. And this is a cutting board, which you have at home, and a knife, and I'm going to take some of the red cabbage and just cut it into small pieces, about 2 centimeters or so in size. Do this very carefully so that you don't cut your finger when you're doing the chopping. And the next thing that you do is you get a blender. You have a blender at home? Yes, you do. You take the chopped red cabbage, you put it in a blender, like so, and then you put some water to cover all the red cabbage that you have. Make sure you add enough water so all the red cabbage is covered. And what's the next thing that you do? No, you put the lid on. You have to obey all the safety regulations all the time, right? And then you push the button, and there it goes. And what we've done now is we've made ourselves some red cabbage juice. Not to drink, but to use in a set of experiments. The next thing that you do is you get, what's this? A strainer. And you use a strainer to separate the red cabbage juice from the rest of the red cabbage. And it goes down like so. You think you can do all this at home? Yeah. It's a very, very straightforward and simple experiment to do, yet it is a very colorful experiment. Well, we'll see if it's colorful or not. So far, we just have the color of the red cabbage juice. And what we want to do is add some more water so we have more red cabbage juice. The next thing that we do is we take a group of beakers or plastic cups that you might have at home, and you put some of the red cabbage juice into each one of them, like about half or a third of the way full. It doesn't matter how much you put in, as long as the level is about the same. Now, you're keeping an eye on what I'm doing. Make sure that the level is about the same. Is the level about the same in all of them? Yes? Some people say yes, some people say no. Which one needs to be increased? First one? The one on my right? Okay, I'll add a little bit over there. This one here? How am I doing so far? Okay? All right. Now, what you do next is take another chemical that you have around the house, and that's vinegar. You take vinegar and you add it to the second beaker, and you see a pretty color develop because red cabbage juice also is an acid-base indicator. This is the color of red cabbage juice when you have an acidic substance. Vinegar has in it acetic acid. Next, you take household ammonia, and you add household ammonia to, and that gives you the characteristic color of red cabbage juice with a basic substance. Then you can try just about any substance you have at home, any chemical you have at home, to see if it's acidic or basic. Do you think this is going to be acidic or basic? Well, it's a carbonated beverage. It has in it carbonated water, so chances are it is going to be acidic. How do we find out? We do the experiment, right? We just add some. There it is. And you see the color is on the acid side. You also see a lot of foaming. That's the carbon dioxide that's dissolved in the soft drink. What about something like a detergent? Do you think that's going to be acidic or basic? Oh, don't guess. It's a 50-50 guess, right? So just think about it, all right? So, and we add some over here. And then we take a little, you take a spoon or a glass rod, as I have here, stir it up, and you see the color is on the basic side. So you're right, it is basic. What about something like milk? You think that's basic or acidic? Well, you're not sure, are you? So how do we find out? We try it. We do the experiment. So we add milk. Well, you see, we have a small problem here. The color of the milk itself interferes with this test. So one of the important things that we have to keep in mind when we do experiments is to be sure that we select substances, number one, that dissolve in water, and number two, that their own color does not interfere with the test that's being used. That's why I used this soft drink rather than another colored soft drink. What about baking soda? You think that's acidic or basic? Well, let's try it. And the color is on the basic side. How about something like Drano? Is that acidic or basic? All right, well, let's try some. And we see that Drano is on the basic side of things. In general, not always, but in general, things that we eat are acidic, and things that we do not put in our mouths are basic. But in general, that's not always necessarily the case.
In case you didn't get a chance to write all that down, here's a list of materials you will need to perform the acid-base indicator experiment at home. 1 red cabbage, 8 clear plastic cups, water, vinegar, ammonia, a carbonated beverage, milk, baking soda, and Drano. Have fun!